playing back and forth is what you're sort of listening to. Now, if this is spot on, you won't hear it at all. And if it's a little bit off, you're more apt to hear it. What I was hoping to hear was some sort of trill, just to say that how close we, give some sense of how close we were. But I didn't hear the trill that time. All right, I'm gonna take one more shot at this, and then we're gonna have to use theater of the imagination. All right, so.
Blessed assurance is talking about those.
You say what?
Blessed assurance.
Most wonderfully fine.
Most wonderfully fine.
All right, let's do the next one. See how close we get. It usually gets worse, so it really can't get worse than that one. Or maybe you guys could hear it and I couldn't.
I mean, I thought I was just like not getting it or not knowing what I was hearing for, but like I did hear a skip, but it wasn't like I thought that was maybe because you weren't doing it consistently.
That could be too. All right, let's try to check out the third harmonic, and then we will. L equals. One should be 1.5. Yeah, 1.5 wavelengths. So the wavelength is going to be 2/3 L. L being 0.845. What is the wavelength? Times 2/3.
I got 0.563277.
563,277. All right.
And that time.
And then 340 divided by that.
Okay. 603.6106.
Which is just the sum of the previous two.
Because that's what it's supposed to be.
It should be
Around.
It should actually be the sum of that, just from the nature of the fact that this is 2/3 the length. Yes, thank you. All right, so the next harmonic. So 604 is the closest. Keep that in mind. Those actually sound more similar. There actually is an extra trill there. Without that. Okay, maybe not.
That's what I was hearing.
I'm hearing a trill there.
Yeah.
It's second or third. I am hearing an extra trill in there with that displaying at the same time. I don't know if you are. Okay,
Just doesn't sound.
Jack's got my back.
I got it.
The rest of you? Well, I hope that at least gives you some confidence that what I'm telling you is true.
It's a real thing, I swear.
Yeah.
I'm not making it up this time, guys.
Unlike momentum.
And all the other things.
Anyway, questions? All right, so as sound is produced, it sends out waves. So, because I can't quite figure out how to work that, and there is no owner's manual that they provided to us. I know I can look it up. This is going to represent a very still pond, and a rock has gotten thrown in that spot.
I was just about to ask, if we think about sound waves, I know we can't see them, but like just how they work, and then like actual water, do they work similarly or the same?
As sound waves and
Like water, like if you're talking about like a pond on water or a rock pond.
for waves, there are definitely some similarities. I mean, they have some speed depending upon the medium. There's constructive, destructive interference. They can, depending upon how you set it up, sound waves can definitely, well, actually anything can be modeled with sine and cosine waves. Known as 48 transforms. Was your question close enough to answer?
Yeah.
Okay. So this represents a very still pond. You throw a rock, and that rock's going to send out, basically there's going to be a ripple here. So at some time later, there's going to be, actually, gotta go sideways. That ripple will now be to there, and then a little bit of time later, it'll be there, and then that ripple is just going to grow. At some set time later, you throw another rock in the exact same spot because you are that good. So there's going to be a second rock that gets thrown right smack dab in the middle, and then that wave is going to grow and grow. And then the exact same amount of time later, you're going to throw another rock smack dab in the exact same spot because, as mentioned before,
You're that good.
that's right. And then that's going to grow. So there's definitely a wavelength here. There's a period, there's repetitive motion. The wavelength would be the distance from here to here, which should be the same distance from there to there if drawn properly. Which is, again, if all of these have the exact same period, all of these wavelengths should be the same. Period is how often the rock hits that spot, and the frequency would just be the reciprocal of that. Amplitude would be how big the splash is, so it would be sort of dimensioned in this direction. All right, questions about my beautiful artistic drawing? All right, so next one, we're going to throw that first rock in the exact same spot. The water has now calmed, cleared. Throw the rock here, and that wave's going to get bigger and bigger, and so on. The next rock is going to be thrown off to the right. So this is where the first rock hit right here, but the second rock is going to hit in this spot. And so the center of the next wave is in a different spot. So now we have different wavelengths depending upon where you're standing. Over here, we have a wavelength that far, and over here, we have a wavelength that far. Well, the speed of the wave in both cases is the same because the water is the same. But if I have a different wavelength, what does that mean in terms of the frequency?
Frequency is no longer the same.
which is going to have a higher frequency.
The shorter distance.
This side?
Yeah.
Yeah. If you were a bug on the water here, you'd be hit by these waves more frequently than if you were over there. Same thing happens with sound. As an object is moving towards you, you will hear a higher frequency than when it's moving away from you. Otherwise known as the Doppler effect. So as an object approaches you, you get a higher frequency. So the wavelength goes down, frequency goes up. Now, I know what you're thinking. All of this has just been absolutely fascinating. However, we need more math. So let's do that.
The nail on the head now.
I can read my route. All right, so I send a wave out. It's going to travel this far. So whatever the speed of the sound is, so I'll put v sub s for the speed of sound, times the period, that is that distance. Now the second wave, so that's where the first one was sent. The second wave, so if my source is moving, so we'll put E for emitter. Emitter moving velocity to the right. So I have however fast the emitter is traveling. It's going to travel this distance, which should be VE times the period. So he lets off the sound, and then he lets in whatever the period is, he lets off a sound again. So the wavelength from the emitter's point of view, or sorry, the wavelength from the bug on the water's point of view, or some person standing here, that is going to be the wavelength that the observer or the receiver would be lambda sub r for the receiver. So I know that lambda sub r is going to be how far the wave traveled, this full distance, minus how far the emitter moved. I've got a mixture of stuff. This was the period from the emitter's point of view. So R for receiver, S for sound, E for emitter. I know that V is equal to frequency times the wavelength. That's the speed of whatever. So the wavelength, so this is the speed the receiver knows. Do it. Oh, yeah. So this would be speed of sound, frequency the receiver catches, and wavelength the receiver catches. So the wavelength here is going to be the speed of sound divided by the frequency the receiver detects. That's going to be equal to V sub S over the frequency from the emitter's point of view minus V sub E over the frequency from the emitter's point of view. This is not necessarily the nicest form of it, so let's do a little algebra. So let's get the frequencies by themselves. So I have, therefore, Vs over the frequency that the receiver picks up is equal to 1 over the frequency of the emitter times the speed of sound minus the speed the emitter is going. We take the reciprocal of both sides, so I have the frequency the receiver is picking up over the speed of sound is equal to the frequency the emitter is sending out over speed of sound over the speed of the emitter. And so the frequency that the receiver is hearing is going to be equal to the frequency that the emitter gives off times the speed of sound over the speed of sound minus the speed of the emitter. This is set up as if the emitter is heading towards the receiver. You're heading towards the person in the middle of the road, honking your horn. So if you have a horn that beeps at 440 hertz, and you are traveling at 30 meters per second, so you're having 30 meters per second towards the observer, speed of sound will go with the 340. Technically, these are all meters per second, which would then cancel out. And if you go through the fancy math there, you end up with what the frequency is being heard. Well,
Where'd you get 30 from?
In the problem I said, you're in a car going 30 meters per second, about a little over 60 miles an hour.
I got 482.58 hertz.
So you in the car, because the sound is going your same speed, it's at rest relative to you, you will hear 440 hertz, but the bystander or the person in the middle of the road will hear 482.
That's good.
Once you pass the person, so you're now going away from the observer, it'd be 440 hertz times 340 over 340 plus 30.
This might be a silly question, but can you have negative hertz?
No, I've never seen any meaning assigned to that.
Okay.
There might be some bizarre quantum thing, but I have not run across it.
Just very quiet.
It's like negative mass. There is some theoretical basis for such a thing to exist. Does it really? Yeah. So if you're heading away from the observer, what's the new frequency? And I might have mentioned this before, I use frequency and pitch interchangeably. I know officially frequency is a description of the sound wave, pitch is a description of what you hear. I also use them interchangeably.
404.32.
So heading towards you, as it passes, it drops off. Now, suppose the observer is heading towards you. You're sitting in the driveway, you're pushing down on the horn for whatever reason, because you're doing a physics experiment, and somebody in a car is zipping towards you in your driveway, going at 30 meters per second. Well, that's not taken into account here, but I will hand wave to it. So the frequency the receiver hears is equal to the frequency from the emitter times the speed of sound plus speed of the receiver. So if the receiver's moving, it goes on top. If the emitter is moving, it goes on the bottom.
Useful.
So what you will sometimes see, and so the frequency that you would hear, assuming you have still 440 hertz, would be 340 plus 30 over 340.
Would that not be this? No. I got 478.82.
So notice it is different by about 4 hertz if you're heading towards the person hearing it or versus the person observing it is heading towards you. We can then generically come up with an equation. Oops, sorry.
You had plus minus.
Correct.
Why?
if he's heading towards me, he's going to hear a higher frequency. So the way that the formula sometimes is presented is that the frequency that's being received is equal to the frequency being emitted times Vs plus minus Vr over Vs minus plus Ve. Something along those lines. I've seen tables in some books where, given the different scenarios about when you use plus, when you use minus, I always find those confusing. What you really need to do is think about, all right, are they getting closer to each other? All right, if they're getting closer to each other, I know that the frequency has to be higher. Well, I'll make a higher frequency, so if the person's coming towards me, the receiver's coming towards me, well, I know I need to add because that'll get a higher frequency. If I'm going towards the observer, I'll need to subtract in the denominator. And then vice versa. If I'm chasing the person and we're both going the same speed, well, one's plus, one's minus. I guess if I'm if I'm the emitter and I'm chasing the receiver, it'll be minus on the bottom and, I misspoke earlier. Minus on the bottom, minus on the top. Minus on the bottom because I'm getting closer. I'm heading towards them. Minus on the top because the person is going away from me. And you end up with, you hear the same thing. If they're both negative or positive. Anyway, think through it. And that will tell you what sign to use. Which I find a whole lot easier than looking at memorizing some table. Yeah.
Go towards them. Away from them.
I didn't catch all of that, so I could just nod, go, sure. Or
towards them. Going towards somebody stationary. It's got to add.
You want a higher frequency.
Higher frequency. Away from them.
You want a lower frequency.
Makes sense.
Yep.
Logic.
And if you've ever been on the side of the road when a car goes by and you get that, it's higher when it's coming towards you, lower when it's going away from you. Life might help.
Oh, can we find the frequency of an engine?